Hello U12, here we are with our first dot point of maintaining a balance. It is identify the role of enzymes in metabolism, describe their chemical composition, and use a simple model to describe their specificity on substrates. So, one of the skills that we're going to try and develop over the coming year is to learn how to unpack the dot point. So the first dot point that we have here has a couple of verbs. The first one is identify, the second one is describe, and the third one here is use a simple model to describe. And so we want to be able to readily identify these things. So when I have a dot point up on the screen, it will be bolded for those verbs. The underlined words here that you have in front of you are these are our content that we are trying to learn about in these dot points. So here we need to learn about the role of enzymes. We need to understand their chemical composition, and we need to understand this concept called specificity. The words that have been italicized, that's the context that we've got to learn these in. So we need to know the role of enzymes in metabolism, and we have to understand specificity in terms of their effect on substrates. So hopefully we can see a pattern as we go along with this. Alrighty, so we've got to start with a couple of basic definitions first up. Our first one is metabolism. So metabolism is the sum of all the biochemical reactions occurring in the cells of the body. Basically, you might have heard previously that people can have a fast or a slow metabolism. And in this context, we really just want to talk about any cellular process that occurs in the body that sustains life. We whack that under the heading of metabolism. Alright, so we're going to introduce this word called an enzyme today. So you might have heard some enzymes in like cleaning products, which is cool if they work. So what they are though, they are proteins, and they act as this biological catalyst, and that's a concept that we're going to explore a little bit further on. So a catalyst. And we're going to talk about the second dot point here first. So a catalyst regulates the speed of a reaction. In most cases in the body, this actually means speeding up the reaction so it can sustain life. Most reactions in the body would take years to complete at the amount that we would need them if it wasn't for the case of enzymes. So that leads into that first dot point, which is without enzymes, metabolic reactions would be far too slow to support life. Cool thing about enzymes too is they're not actually used up in these reactions. You can use them over and over and over again. So so long as that protein is still functional, the enzyme is still functional, and so the body doesn't have to mass produce these things. Okay, so we're going to talk about proteins now. So proteins are large globular molecules. They have a three-dimensional shape, and they are commonly described as folded polypeptide chains. A polypeptide chain is a long chain of amino acids that are joined together by something called a peptide bond. Later on in the course, we will explore peptide bonds quite specifically, and hopefully you'll kind of be able to make some links back to this dot point. In order to recognize an enzyme, if you ever see one thrown about, they generally have the ending A's. The one that I've given here is amylase, that is in the mouth, and you find it in saliva. You might have other ones that you might come across as well. Okay, here we have this three-dimensional shape. It contains an area. It could be a large area, it could be a small area, but whatever the area is that is functional, we call that the active site, and that's where the enzyme does its job by bonding to a substrate. A substrate is the molecule that the enzyme acts on. So an enzyme will either break a substrate apart into smaller molecules or force two or more substrates together to create a larger molecule. Because of this 3D shape, they're kind of like a key. So they are highly specific to the reactions that they can catalyze. The shape of the active site will determine what type of substrate can act upon it. And in order to kind of um, demonstrate this specificity, scientists use models to show them. So the first model that we're going to look at is the lock and key model, the most common model used to describe specificity. This is quite a good model um, in order for you guys to understand kind of like a key fitting into a lock. You kind of get that keys are designed for a particular lock, so you kind of understand that. But what we need to use this model to do is to understand what's going on with the actual process too. So when an enzyme acts upon two different substrates, a enzyme substrate complex occurs, and after placing physical and chemical stress on the molecules, a new product is formed. This process can go both ways, and the enzyme can act on a single substrate, form the complex, and then break them up. So as you can see, the enzyme here is not getting used up in the process, it's just doing its job, and then will be available to act on another substrate. The next model that we've got here is the induced fit model, and it's kind of like the lock and key. It looks very similar. It's got a lot of similarities here, but you'll notice that the enzyme in the first section, first diagram here, is less defined, and so often when a substrate comes along, an enzyme can change its shape slightly, this induced fit. So the substrate binds to an active site, the binding induces a temporary change in the shape of the enzyme, this is the induced fit, a chemical reaction occurs, and the substrate is changed and the product is released. The enzyme will then kind of return back to its normal shape, and just like in the previous model, can be reused to bind with another substrate or substrates. Both models, I think, do a really good job of explaining specificity, but with the induced model, we can kind of see that maybe their enzyme has less specificity. So there are a couple of enzymes in the body that can be used in multiple reactions. They're not common, but at least this model recognizes the ability of that to be able to happen in the body. So, quick look at these models and advantages and limitations of these models. The first one, it's simple. It really works with that kind of idea of the lock, and it works that way. The limitation of the lock and key model is the big one is that we don't understand what time frame this occurs in, and doesn't take into consideration that some enzymes aren't as specific as we once first thought they are. The induced fit model is currently considered one of the most accurate models, but at the moment the evidence to show this at a molecular level is building. So it's that evidence body is it's a new kind of model. So we're going to try and find some evidence for that one. And just like the lock and key model, we have a lack of a time frame. So let's try and summarize this. You've been good. You've worked your way through to the end here. So, number one, enzymes are proteins that catalyze metabolic reactions. They're large with unique shapes, and the active site defines the substrate that they can act on. This makes them highly specific. Scientists use models to represent this specificity, and the two that we are learning about is the lock and key model and the induced fit model. Thanks for listening, guys, and hopefully that makes sense. If you need to revisit this, please do. Don't forget, you can always stop, rewind, take a loo break. It's all good stuff. Alright, thank you very much.